students, welcome to another lecture in our course Environmental Modeling and Simulation. Today we are going to revisit 2D systems and we are going to look at some examples, some unique cases, and then we are going to use this 2D linear system understanding to explore 2D nonlinear systems. So let's get started. Some of the interesting cases that we saw in the previous lecture were when your eigenvalues become same. So that was the case when A was equal to -1, which was one of the eigenvalues, and the second eigenvalue was also -1. So in this case what we saw was a star node. Now let's try to understand from a little analytical perspective what happens when your eigenvalues are same. So remember, in the previous lecture I told you that the solutions are basically C1 E lambda 1 t V1 plus C2 E lambda 2 t V2, right? These are the solutions for our 2D system. Now what happens when lambda 1 is equal to lambda 2? So let's substitute lambda 1, lambda 2 for a generic lambda. So what happens now, we have a solution that looks like this. Okay, we can take E lambda t common. So now we have C1 V1 plus C2 V2. Any linear combination of our eigenvectors is also going to give us a solution. So now in this case what we have is we don't have a single eigenvector, we have multiple eigenvectors. If you remember in 2D systems, let's say this is eigenvector V1 and let's say this is eigenvector V2. If an initial point is sitting on any of these eigenvector, then the trajectory will be coincident with the eigenvector, will be a line that will be coincident with the given eigenvector. In this case, when lambda 1 is equal to lambda 2, any linear combination of these two eigenvectors V1, V2 is also an eigenvector for you. So basically all trajectories become your eigenvector. So what it looks like is, let's say this is your initial value, then connect this to your fixed point and lo and behold this is your new eigenvector. So any initial point on this line will follow this eigenvector. So that's why what we end up here is getting something like a star node. So I didn't explain this in the previous lecture and I wanted to make sure that you understand the logic behind why we get star node when lambda 1 is equal to lambda 2. When lambda 1 is equal to lambda 2. Another example that we saw which was very fascinating was when one of the eigenvalues became 0. So let's see what happens when one of the eigenvalues becomes 0. When one of the eigenvalues becomes 0, basically in the direction corresponding to the in the eigenvector direction corresponding to lambda 1 which has become 0, there will be no movement. So what we get in this case is either a line of fixed point or we get a plane of fixed points. If both eigenvalues become 0, so we are dealing with a situation when we have a plane of fixed points, nothing is changing. If only one eigenvalue is 0, then we have a line of fixed point. Now, sometimes a very interesting third situation happens which we didn't see in the previous lecture. That is when we only get one valid eigenvector, we don't have the second eigenvector. So this is the third situation that we are dealing with when only one eigenvector is present. So when there is only one eigenvector present, what the trajectories do is they eventually move towards the fixed point or away from the fixed point, and as they approach or move away from the fixed point, they become tangential to the only available eigenvector. So the movement looks something like this. Let's say V1 is the only available eigenvector. Yeah, and to make life a little easy for me to draw, let's say the corresponding eigenvalue here is negative. So we are dealing with a stable node, lambda 1 and lambda 2 both are less than 0. So clearly the flow in the direction of eigenvector will be towards the fixed point. Now let's say we are having a starting point here. So what will happen is that this trajectory will move, and as it moves, as this phase point moves, as it approaches the fixed point, it will become tangential to the only available eigenvector. So our flow lines look like this. Now this looks like a very confusing movement because near the fixed point we see dramatic change. It's still continuous, it's still smooth, but there is a dramatic change in the direction of our trajectories. Such a node is known as degenerate node. Now one way to understand a degenerate node is not to think that, oh, one eigenvector does not exist, but to think that both eigenvectors are now coinciding. So we have a situation where v1 is equal to v2 is equal to v, the only available eigenvector. So if you look at it from analytical perspective, we are in a situation where the solution is common eigenvector. So the flow will happen corresponding to lambda 1, lambda 2, but it will be in the direction eventually of the only available eigenvector. This is a very interesting kind of situation that we run into sometimes. Now what we can do is we can build upon our current knowledge of how 2D systems work and how to interpret them to understand how to solve the questions pretty quickly, the questions that you'll get in the exam and the questions you will face in your real life when you're applying the principles from here. Okay, so let's use the principles that we already know and try to understand how system works. Let's start with a very simple example. Okay, so let's say we have a system like this. Okay, and we can find the eigenvalues using characteristic equation, and let's say the eigenvalues that we find are lambda 1, lambda 2 and the corresponding eigenvectors are v1, v2. We already know this, that if lambda 1 and lambda 2 both are less than 0, we are dealing with a stable node. If both are positive, we are dealing with an unstable node. If one of them is equal to 0, we are dealing with a situation where we have line of fixed points. When both of them have different signs, one is positive, one is negative, then we are dealing with a saddle node. And then this is a line of fixed points. And when they are a complex number, then the real part of the lambda will inform us regarding the kind of spiral we are dealing with. So if it's a complex lambda 1, lambda 2 that we get, we are dealing with either an inward moving spiral or an outbound spiral. If the real part is 0, so it's a purely imaginary eigenvalue, then we are dealing with center closed orbits. So this we already know. So let's summarize this. So here, when we are trying to find out our lambda values, let's say A is equal to A, B, C, D. Then the characteristic equation is okay. So when you open this quadratic equation, what we'll end up is with a system that looks like so. Right, I am defining tau as trace of our matrix A and delta as the determinant of our matrix A. So tau is equal to A plus D and determinant is given by AD minus BC. Now since this is the quadratic equation we get, we also know something else about tau and delta, that tau is basically lambda 1 plus lambda 2 and determinant delta is lambda 1 into lambda 2. Okay, so we can combine what we know about the behavior of our nodes according to lambda 1, lambda 2 into what we now have defined as trace and delta, determinant of our matrix A. So let's look at the first situation when we have a stable node. When we have a stable node, lambda 1 and lambda 2 are less than 0, which means in case of stable node, our tau will be less than 0 because lambda 1 plus lambda 2 will be less than 0. However, the determinant will be greater than 0. So if you are dealing with a situation where tau is less than 0 and determinant is greater than 0, then we might be dealing with a stable node. Not exactly, but we might be dealing with a stable node. Now let's look at an unstable node situation. In an unstable node situation, both lambda 1 and lambda 2 are positive, which means if your tau is positive and delta is positive, because lambda 1 plus lambda 2 will be positive, lambda 1 into lambda 2 will be positive, then we might be dealing with an unstable node. Now, when lambda 1 is equal to 0, so you are dealing with a line of fixed point or a plane of fixed point, then your delta will become equal to 0. Now, when you are dealing with a saddle node, what will happen is your delta will be negative, because one eigenvalue is negative, another eigenvalue is positive. So, the product of two eigenvalues, which is the determinant of the matrix A, will become less than 0. Now, what will happen when we are, oh, now this is interesting. Why did I say that this will not always be the case? Because if your eigenvalues are real, purely real, then this will be the case. But if they are not real, then we are dealing with inbound spiral, outbound spiral, and centers or closed orbits. So, to make that more clear how the system will behave, so when will it be spiral, when will it be center? Let us go back to our quadratic equation. Eigenvalue square minus tau eigenvalue plus delta is equal to 0. The solution to this will be given by tau plus minus under root tau square minus 4 delta divided by 1, Sridharacharya's rule. So, if what is inside this bracket, which is tau square minus 4 delta, if tau square minus 4 delta is less than 0, then this eigenvalue 1 and 2 will become complex. If tau square minus 4 delta is less than 0, but tau is not 0, then we are dealing with complex eigenvalues. If tau is 0, then we are dealing with purely imaginary eigenvalues. In that case, we are dealing with orbits, we are dealing with centers. So, we can add on to this list. If tau is equal to 0, if tau is equal to 0, lambda 1 plus lambda 2 is equal to 0, or the trace of your matrix, your A, is equal to 0, in that case, we are dealing with orbits, we are dealing with fixed orbits, we are dealing with centers. If tau square minus 4 delta is less than 0, so you also need to look at the sign of tau square minus 4 delta, then we are dealing with spirals. So, the spirals when tau is not equal to 0. So, here tau is equal to 0, here tau is not equal to 0, but tau square minus 4 delta is less than 0. For all these situations here that I mentioned earlier, tau square minus 4 delta should be greater than 0. We can summarize this understanding in a very simple graph. Here is our graph. So, let us try to understand this graph. Let us remember that tau is the trace of your matrix, it is lambda 1 plus lambda 2. It also, since it is the trace of matrix A, gives A plus T. Delta is the product of two eigenvalues, and we get it by AD minus BC. Okay? Now, let us look at this diagram. Now, what happens when tau is equal to 0? When tau is equal to 0, we are dealing with only x axis. So, tau is equal to 0, lambda 1, lambda 2, when they add up, A plus D is equal to 0, we are dealing with centers. How does it make sense? Because remember, lambda 1, lambda 2 are given by tau plus minus under root tau square minus 4 delta. So, what we have here is tau is equal to 0. So, lambda 1 lambda 2 is basically minus 4 delta. So, we have 2 under root delta I magnitude. So, this is a purely imaginary eigenvalue, which means around the center there will be no net movement away or towards the fixed point. So, let us say this is our fixed point. There will be no net movement away or towards from the fixed point. The phase point will keep moving around the fixed point. Now, the direction of this movement, whether it is clockwise or anti-clockwise, we can very easily calculate it by putting it in our solution. Remember, solution is equal to C1 E lambda 1 T V1 C2 E lambda 2 T V2. We can use this very simple expansion that we know, and we can do some very simple calculations to figure out the direction of the movement. Okay, now let us look at the case of stable nodes. So, we are dealing with stable nodes. What is happening in stable nodes? First things first, tau square minus 4 delta is greater than 0, which means if we draw a curve, so this curve that you see here, this line is basically tau square minus 4 delta. Any point inside the curve corresponds to the situation when tau square minus 4 delta is less than 0. So, this is where we are dealing with complex or imaginary eigenvalues. Okay. In tau square minus 4 delta, we are talking about all the points that are outside this curve. In this case, we are dealing with real, purely real eigenvalues. Now, if tau is negative, but your delta is positive, right? So, we are dealing with this particular place. Let me color it. Right? So, notice delta is positive, we are in the fourth quadrant. Tau is negative because we are in the fourth quadrant and we are outside the curve. So, in this situation, what we have is tau is negative, sum of your eigenvalues is negative, your delta is positive, product is positive. So, you have both eigenvalues less than 0, your eigenvalues are real because they are outside the curve, we are dealing with stable nodes. Similarly, when we are dealing with this particular situation, this is where tau and delta are both positive and tau square minus delta is greater than, tau square minus 4 delta is greater than 0. Both eigenvalues are real and they are positive, we are dealing with unstable nodes. Now, when tau and delta are positive, but we are inside the curve, we are in the domain of unstable spirals. When tau and delta are, when delta is positive but tau is negative and we are inside the curve, which is tau square minus 4 delta is less than 0, so we are dealing with stable spirals. When we are on the line, which is the x-axis line in this graph, we are dealing with centers because tau is 0. Now, what happens when we are in the second and third quadrant? In second and third quadrant, there is no situation for us to have imaginary, there is no possibility for us to have complex or imaginary eigenvalues. We have real eigenvalues, and here, regardless of the sign of tau, your delta is negative. So, anytime your delta is less than 0, you have entered second or the third quadrant. In that case, we are talking about saddle points. Remember, delta is product of your eigenvalues. The product of your eigenvalues is less than 0. Okay, which means one of your eigenvalues is negative, the other is positive, definitely a saddle point. Now, what happens when regardless of your tau, your delta is equal to 0? When delta is equal to 0, it means one of your eigenvalues is 0. So, this is when we are dealing with a line of fixed points or a plane of fixed points, because the growth or decay in one direction corresponding to one eigenvector has become 0. If you look at this diagram, when delta is equal to 0, we are now limited to the y-axis. So, regardless of where we are dealing with non-isolated fixed points. They are non-isolated, they are connected with each other. We have infinite fixed points now. So, either we have all the non-isolated fixed points on a line or in the entire plane. Okay, this is a very important diagram. I hope you have gathered it. Even if you can just calculate tau and delta, and I am going to walk you through how to do it. So, let me erase this, clean this up. So, even if you can just calculate the values of tau and delta, you can very quickly understand what the behavior is, even without calculating lambda 1, lambda 2, even without calculating the eigenvectors using the analytical approach. So, as a reminder, let us not forget tau is the trace of the matrix, so it is A plus D. It is also the sum of our eigenvalues. Delta is determinant of the matrix A, so it is AD minus BC. It is also the product of our eigenvalues, lambda 1 into lambda 2. Okay, so let us take a very simple example where we have a situation like so. So, this is, yeah, make it simple. Okay. So, we have this situation. Even without finding eigenvalues and eigenvector, we can very quickly find the trace and determinant. What is the trace here? A plus D, 1 plus 4 is equal to 5. What is the determinant here? AD minus BC. What is this? So notice here your tau is positive, your determinant is negative. Here the tau is positive, the delta is negative. So we are so where are we? We are in the second quadrant. We are talking about saddle node. So even without finding out what lambda 1 is, what V1 is, I know it's a saddle node. Now in case of saddle node, it's very helpful to find out eigenvectors. Why? Because then you will know whether your saddle node is moving around these two eigenvectors or it's moving around these two eigenvectors. Or if your one eigenvector has collapsed into another and you're dealing with a degenerate node. Okay. Well, by the way, it's very easy to find out the degenerate nodes. Degenerate nodes are typically in this situation and they lie on the line. That's when your eigenvector, one of the eigenvector collapses into the other on the line of the curve. Okay, let's take another example. So I'll keep the system same. Let's call it 2, 1, 3, 4. Yeah, 1, 2, 3, 4. Going this way now. Okay, what is your trace here? The trace is 6. It is greater than 0. So we're definitely dealing with first or with the second quadrant. What's the determinant here? 2 into 4 minus 3 into 1. That is 8 minus 3. So we're dealing with 5, which is also positive. So now we are in the first quadrant. So we're dealing with first quadrant. Now, don't jump into conclusion and say, oh, this is an unstable node. Because clearly tau is positive and delta is positive. So lambda 1 and lambda 2 are positive. Let's find out whether it is below the curve, this tau square minus 4 delta curve, above the curve or on the curve. So to do that, let's calculate tau square minus 4 delta, which in this case will be 6 square minus 4 into 5. So we have 36 minus 20, 16, which is bigger than 0. So we know that our point lies above the curve in the domain of unstable node. So just by using this diagram, by finding out tau value, by finding out delta value, and then depending if we are in the second or if we are in the first or fourth quadrant, then we also need to calculate tau square minus 4 delta. We can use this graph to understand whether we are dealing with unstable node, unstable spiral, center, stable spiral or stable node. Memorize this plot, it will be very helpful for you. Alright students, this is all for today's lecture. In the next lecture, we will start looking at a very simple example of how we can model human relationships using 2D linear systems. And I'm very excited to teach that because that's where the examples become very fun. We'll be talking about two friends, A and B, and how their relationship we can understand by looking at the matrix A, the coefficient matrix. Alright, I hope you're as excited about it as I am. See you in the next lecture. Thank you.